In this video, we're going to consider a rotor with the following properties. The mass is in plane 1, 2, 3, 4 with a magnitude of 9786 kg and radius of 100, 120, 140 and 120 millimeters. The angular position is 0, 60, 130, 5 and 270 degrees. The axial distance from first mass is from first mass to mass 2 is 160 degrees, from mass 1 to mass 3 is 320 degrees, and to mass 4 is 560 degrees. If the shaft is balanced by two counter masses located at 100 millimeter radii and revolving in planes midway of plane 1 and plane 2 and midway of plane 3 and plane 4, determine the magnitude of the masses and their respective angular positions. So you know that the first step is to tabulate the given data. Here we're going to include couples since we're given the axial distance. So the second step is to draw the first polygon, and you know that the third step is to start resolving. So we're going to resolve the centrifugal force and the couples. So because we have axial distance here, so couple is also going to be included in our solution. So from the table we have that the mass, our counter mass is the first counter mass is between mass 1 and mass 2, which is here. So we make mass M, we'll call it mass M. So mass at position M is between mass 1 and mass 2. Then the second mass is between plane 3 and plane 4, which is mass N. So you have the value of masses. Then the radius is converted to meters because it is given in millimeter. It is in millimeters. So you have the value in meters. Then the column for force. The force is mass times radius, which is the magnitude of mass times radius. So you have these values here. Then the axial distance is minus 0.16. So I'm going to explain why this one is negative from our position of planes of masses. So we're going to talk about that later. I will explain it. Then we have the couple, which is mass times radius times length, which is given below. Then you have the angular positions, which is theta from theta 1 from position 1, 0. Then for the position M is theta M because it is unknown. Then you have theta for the second position 60 degrees, 130, theta N for the counter mass at position N, and 270 for the fourth mass. Then the second step is to draw the first polygon of vector diagram. So you have that from mass 1, which is at 0 degrees, to mass 2 is 60 degrees. Then from mass 3 to mass 1 is 135 degrees. From mass 1 to mass 4 is 270 degrees, which is 90 degrees anti-clockwise. So that's how I have 90 degrees here. So balancing for dynamic balancing, the conditions required are sigma mr, which is summation of forces plus summation of force at position M plus summation of the force at position M and plus force at position N is equal to 0. So for the couple, which is summation of couples plus the couple at position N, so we choose mass M to be our reference point. So we choose mass M to be our reference point, so we'll be able to solve the equation. Because if we choose mass 1 to be our reference point, that means we're also going to have mass M R L M. Here we're going to have like 4 equations, and it will be too complex for us to solve. So we chose mass M to be our reference point. So from the angle of position of planes of masses, let's explain how the axial distance of mass 1 is why it is negative. So we choose mass position M to be our reference point, and it is located midway, that's at the middle of the position of plane 1 and plane 2. And from plane 1 to plane 2 is 160 millimeters. So from plane 1 to plane M, which is at the middle of which is at the midway of 1 and 2, is 80 millimeters. That's half of 160 millimeters. So since here is our reference point, and you know our reference point is from the 0 point, that's where you start counting. So here is 0. So since minus 1 is behind our reference point, it means that the distance is negative. So that's why you have minus 0.08 in the table. So from mass 3 to mass 1 from mass 3 to mass 1 is 320 millimeters. So which means that from here to from mass m, from our reference point to mass 3 will be 320 minus 80 millimeters. The same goes with mass m. So mass n is located between mass 3 and mass 4. So and the distance from mass 3 to mass 4 is 240 millimeters, which is 560 minus 320. You have 240 millimeters. So middle of these 240 millimeters is 120. So when you add 120 to 320, you have 440 millimeters. So from mass 1 to mass n is 440 millimeters. So from mass n to our reference point will be 440 millimeters minus 80. So you have these values. So that's how we got these values here for the axial distance. So the next step is to resolve the couples into horizontal and vertical components. So we can easily solve couple because here we have only one unknown position. So that's why we're going to resolve the couple first. So we have resolving the horizontal component of the couple. So we have that summation of the couple cos theta plus summation of couple at position n cos theta n is equal to 0. So when you now substitute the value of couple from the table, when you now substitute the value of couple, you have that 0.07 minus 0.072 cos 0 plus 0 plus 0.06672 cos 60 plus 0.2688 cos 135 plus 0.3456 cos 270 plus 0.036 mn cos theta n is equal to 0. So when you punch this in your calculator, you have that 0.036 mn cos theta n is equal to 0.2285. So that will be our first equation. So when we resolve vertically, we have that summation of the vertical couple sin theta plus summation of couple at position n sin theta n is equal to 0. So when we substitute the values of couple in the vertical component, you have that 0.772 sin 0 plus 0.0672 sin 60 plus 0.2688 sin 135 plus 0.3456 sin 270 plus 0.036 mn sin theta n is equal to 0. So when you punch them in your calculator, you have that 0.036 mn sin theta n is equals to 0.09733. So which will give us the second equation. So now, in order to solve for the unknown, we're going to square the first and second equation. So when we square the first equation, you have 0.036 all in brackets square cos squared theta n plus 0.0636 mn all in brackets squared sin squared theta n is equals to the 0.2285 squared plus 0.0973 squared. So, and from trigonometric identity, you know that cos squared theta plus sin squared theta is equal to 1. So when you collect the common terms between these two terms here, when we collect which is 0.036 mn all in brackets squared, when you collect the common term, you have this 0.036 mn squared cos squared theta n plus sin squared theta n, which is equal to 0.2285 squared plus 0.973 squared. So since cos squared theta plus sin squared theta is 1, so this one will go. You have only this value. When you make this subject formula, you have square root of these values, which is root 0.2285 squared plus 0.0973 squared. So making mn subject formula, you have 0.2284 over 0.036, which will give you 6.9 kg. So our mass at position n is 6.9 kg. So in order to find the angular position, you divide equation 2 by equation 1, which will give you 0.036 mn sin theta n over 0.036 mn cos theta n is equal to 0.09733 over 0.2285. So this cancel out. You have sine theta over cos theta, which will give you tan theta n is equal to this 0.9733 divided by 0.2285 will give you 0.4259. So making tan n subject of formula, I have tan inverse of 0.4259, which is 23.07 degrees. So we've gotten to the value of the mass at position n and the angle of the angular position of the counter mass at position n. So we now resolve the forces, the centrifugal force, into the horizontal and vertical component. So summation of all the forces plus summation of force at position n m plus summation of force at position n is equal to 0. So when you put in the value of forces, which is 0.9 cos 0 plus 0.84 cos 60 plus 1.12 cos 135 degrees plus 0.72 cos 270 degrees plus mrn, which we've already gotten, cos theta m plus, we have mrm cos theta m plus 0.1 times 6.9, which is the value of the mass at position n, which is the value of mn cos 23.07, which is the theta n, is equal to 0. That's the first equation. So when you punch it in your calculator at the end of the day, you have that mrm cos theta m is equals to minus 1.1629. So that's our third equation. So when we resolve vertically, you have that you still have the value with sign. So you have 0.9 sine 0 plus 0.84 sine 60 plus 1.12 sine 135 plus 0.72 sine 270 plus mrn sine theta m. So you have 0 plus 0.1 times 6.9 sine 23.07 degrees equal to 0. So when you punch your calculator, you have that mrm sine theta m is equals to minus 0.698. So when you square equation 3 and 4, so you repeat the same process as in equation 1 and 2. So there's no space to start writing the whole process over again. So when you square the both equation, you arrive at mrm is equal to root bracket minus 1.1629 close bracket squared plus minus 1.0698 all bracket squared. So the square root of these values will give you 1.58. So you have the radius at m position is 100 millimeter, which is 0.1. So you have 0.1 mn equals to 1.58. When you make the mass subject of formula, you have 1.58 over 0.1, which will give you 15.8 kg. So when you divide equation 4 by equation 3, just as we did that in equation 1 and 2, we get that tan m is equals to minus 1.069 over minus 1.1629. So theta will be now tan inverse of this value, which will give you that theta m is 222.6. So you have that theta m is 222.6. So that's the end of it. Please hit the subscribe button for more videos. Thank you for watching.